Ladies and gentlemen, welcome here to the technical forum of the group exhibit Hydrogen Fuel Cells and Batteries. I'm very happy to announce to you that right from Washington he's coming to us from the US Department of Energy, Office of Energy Efficiency and Renewable Energy, Dr. Monterey Gardiner. He will talk about electrolyzers and fuel cells supporting renewable energy through grid integration R&D. So here's his presentation we were looking for yesterday. He's now here with us. Very good. Come to the stage.
All right.
We are looking forward to your presentation. Thank you.
Thank you very much for that kind introduction. So I am here definitely a day late, and it took me more than 30 hours in the travel from Washington, D.C., going the wrong direction with mechanical difficulties. But I am happy to be here now. This fair is just amazing. Without further ado, I'll jump into this, but just to introduce myself briefly, for more than a decade I've been involved with hydrogen and fuel cells, starting out at UC Davis and looking at energy storage, managing projects for the Department of Energy for vehicle storage, and then hydrogen delivery. How do we reduce station costs? I came back from a year in Japan, and now I'm looking at energy storage and managing some of the international relations. Okay, there it goes. So today there's a handful of things that I'll discuss. So I'll talk about some of the opportunities and the drivers, why we might be interested in energy storage, a handful of the technologies and past studies that might have been done, and then some of our priorities as we walk forward. And then a little bit about NREL, our National Renewable Energy in Colorado, where we do a lot of testing of systems, and we have a new facility that's been put in place. So this slide is a bit old, but I think it'll show you where the trend is. So within the US, we have 130 gigawatts almost of pumped hydro. So this is probably by far the largest energy storage option that we have. But this is the Ferrari of energy storage. It's the most costly, and it's grandfathered in. It's the cheapest now because it's been built many years ago, decades ago. But now, if you look at new pumped hydro, the costs are much higher than those installed units. It's similar to looking at a coal power plant and the electricity costs from something that's been in the ground for multiple decades. But on the side of new technologies that are coming up, compressed air energy storage is moving forward. Sodium sulfur, we have flywheels. Out in California, where they have a very high renewable energy portfolio standard, it's very similar to Germany's at 33% by 2020. They are testing both flywheels, flow cells, and compressed air and seeing how that can support the grid. So California is kind of a hotbed. So starting in the upper left quadrant, this is a research forecast by Pike Research for what might be needed in the coming years. So you see there's tremendous growth opportunities. So there's been a lot of interest in where energy storage might be going and what technologies to focus on. So from this particular study, it's by far, it looks like compressed air is being a leader in capacity. We have pumped hydro. There's still places in the US where they're looking at developing either new pumped hydro, or as we saw in the last presentation, it can be much cheaper if you retrofit an existing site and you're not doing an environmental impact assessment and so on. So repowering those existing locations. We have advanced batteries, flow cells, sodium sulfur batteries. But this growth of going from just 600 or 500 megawatts in the next year or two to maybe 6 times that. There's just enormous growth potential, and that's what companies are looking for. So in addition to this growth forecast, right, if you just look at renewable energy integration and energy storage, the finances are very difficult to pencil out. But when you have legislation, whether it's zero-emission vehicles or requiring renewable energy or having a price for carbon, all of those working together can promote and ensure that storage is going to move forward. So in 2010, California passed an assembly bill that will require energy storage. So on the order by 2020, 1.3 gigawatts. And if you listen closely, you'll notice that's not energy storage, it's not in gigawatt hours, but in gigawatts. And it's a learning process as they put this legislation in place. So if they can find these utilities in California can find a lower cost way of meeting that either distributed generation or the benefits of integrating renewables, say you have load following natural gas generation, maybe they don't need to do storage. But this legislation will become much more refined over the next few years, and as California looks at moving beyond 33% to 40% or whatever the next RPS number may be, there's going to be much more certainty in where that energy storage requirements might be. So I would definitely stay focused on California if you want to see where energy storage is going in the US. So just to give a picture, and probably most people here are well familiar with this, but you have renewable energy generation on the left side, and generally for this to work, you want it to be curtailed or excess, some low-cost energy that can't be properly utilized. And what I'm going to focus on my talk in is the electrolyzer. So it's very fast reacting, it can ramp up, it can ramp down, and there's a lot of ancillary services and grid support that can be provided. So that's one part of the puzzle. The other side, and what you might most simply think about, is arbitrage. You buy low-cost electricity, you make hydrogen, and then you sell that electricity back to the grid at some higher price. But when you dig down into the economics, the capacity factor of that low-cost renewable, it's much more difficult to make a near-term business case. But if you start looking at other assets, so vehicle fuel has much higher utility than looking at just wholesale electricity. So it's finding those markets where you either have stranded assets. If you look to the US, the Midwest is where all of our wind resources are, and that happens to be also where much of our agriculture is. We call it the Midwest, the breadbasket of America. So if you can find places where you have this intersection between renewables that may not have a full demand, and either a vehicle fuel requirement, fertilizer, or very, very high cost, high value backup power. So if you look at for banks, you look at for different financial institutions, there are institutions that will want that high quality and very stable electricity, and they would be willing to pay for that. If you look here at the bottom right corner, this is something that was put together by the Hawaii Natural Energy Institute for us. And this is looking at the characteristics on the grid of keeping that frequency stabilization right at 60 hertz. So here in Europe or in Germany, it's 50 hertz. Japan, it's split. But you can see here that if you have no storage, this blue line here, your frequency can have a big dip as your variable generation doesn't track exactly what the grid needs. And right now, this valuation is relatively low because we have a lot of historical generation. So when you look at larger coal power plants, natural gas, this provides a certain system elasticity where it can manage those fluctuations in the grid. But as you have more variable generation and fast ramping sources, you don't get that cushion. And so I think definitely in the future, as we go to higher and higher amounts of renewable energy or variable generation on our grid, we're going to find a much higher need and much more value going forward for these ancillary services. And I guess the point of that is the black line, if you have a megawatt a minute, so if you look at an electrolyzer, and we've seen a lot of companies announcing or coming out with megawatt PEM scale units, you can see that that can very closely load follow, and it manages that excursion. So when you're trying to figure out that valuation, you have to have various metrics. So whether it's the efficiency of a conventional battery storage system that might be very high, the capital cost, right? How often are you storing that electricity? How much of it is low cost? This is just to give you kind of an overview of some of the things that we look at for when we're looking at modeling and trying to justify, say, initial pilot projects or going forward with more detailed projects. So using that analysis as a foundation and baseline for our next steps. So we've seen a lot from EPRI, that's the Electric Power Research Institute in the US. Their stakeholders are utility companies. And they've gone through and they've showed the installed capital costs of several different technologies. And this red bar, which is kind of in the range, this is looking at about 10 megawatts of a stationary fuel cell, an electrolyzer, and then some above ground storage. And all of this is to provide something on the order of 40 megawatt hours worth of storage. But the capital cost is only one part of it, right? You need the input electricities, you need your financial assumptions, your return on investment, and so on. So this is an eye chart, so I don't expect you to read it, but what we were doing is trying to understand where do we need to put our funding for our technologies, right? Do we need to get lower cost fuel cells? Do we need higher efficiency electrolyzers, right? If we're looking at hundreds of megawatts or gigawatts of power generation, right? One alternative might be looking at hydrogen, oxygen combustion turbines if you're looking at really large scale power production. So we have a near term, a distributed fuel cell, 10 megawatts, central fuel cell, something much larger, 150 megawatts, and then a combined cycle turbine, hydrogen, oxygen combustion. And we have various technology targets where either efficiency, cost reduction, or improving over time. And then we have some long-term where we have very aggressive and, depending on who you talk to, some level of realistic target for where we want that technology to get. So this is just based on a very static, just pure arbitrage. So if we look at this, there's underground geologic storage, that's salt caverns. So we have a lot of this in Texas. There's over 1,000 miles of hydrogen pipelines connected to various caverns. And this is primarily to support the oil industry and to ensure that there's no lack of hydrogen. So whether they have hurricanes or other issues, you have energy storage available for you. The green lines that are at a 45-degree slant, that's the cost of above ground storage. So for geologic storage, it's millions of kilograms, and so if you look at it, the additional cost of 1 more kilogram, it's fairly minimal as you look at longer and longer durations of storage. For above ground tank storage, we're looking on the order of $700 a kilogram for an installed cost. We have various technologies, so if we're looking at steel or carbon fiber, or some novel concept is looking at pre-stressed concrete surrounding a stainless steel liner as a low-cost bulk storage option. And then this is compared to a battery. So if you look at past presentations, one of the main advantages of hydrogen and fuel cells is that they scale separately. So if you want to just have additional kilowatt hours, you have a very small cost for your storage, versus when you have a battery where you need more power or you need more kilowatt hours, the whole system scales. And so the costs will increase rapidly as you need more energy storage. So I think as we look to the future, we'll see potentially hybrid systems that can take advantage of that 2 to 4 hours where a battery may be much lower cost. And then when you need a longer duration and somebody's willing to pay for that energy, you might see something with a fuel cell or hydrogen. So this chart is complicated. There's many numbers, but just to break it down, over on the right are near-term costs, and I wouldn't focus on the dollar per 60 per kilowatt hour, but this is just with near-term assessments. And what this was to do was allow us to understand what's the biggest driver if you're looking at a static market of arbitrage, low-cost electricity and selling that hydrogen back. So we have electrolyzer utilization, we have cost, fuel cell efficiency. We need to know where do we put our research dollars and additional funding to see where we can make the biggest impact and accelerate hydrogen for storage to commercial viability. And what we found is you want utilization. So this is the biggest kind of albatross for energy storage, is when you're storing a product, you're not using it. And so when you look through the economics and the financials, unless there's an alternative revenue, that's what's so difficult, is because when you store something, you're not using it, it's sitting on the shelf, it's not being utilized or making you money. So if you find a way where you can have an alternative stream beyond just that curtailed energy, whether you're looking at some bulk power plant, whether it's nuclear systems or coal that can't be turned down at night, I think right now I've heard that in Germany and elsewhere, when you get below that 5,000 hours per year of the 8,000, coal power plants can no longer be economic. So you got to find a way. Where does that energy go for these companies that are losing money because they can't run their equipment? This is a way where electrolyzers can support the general energy industry. So first it was utilization, number one. Two, looking at reducing that electrolyzer cost, the efficiency, and then fuel cell cost and fuel cell efficiency. But again, don't focus on the numbers so much as maybe the priority. And if people have feedback, I'm happy to rearrange these priorities with more input. So if we look at this and put it all together with those past assumptions and looking at some of the storage, you can see if we meet just our midterm targets, we drop our costs really quite a bit. So from $1.50 to 50 cents or so. If we move down to our long-term targets, which are very aggressive, I admit, we might get to around 22 cents a kilowatt hour. And if you looked at new pumped hydro storage, flow batteries, and some of their relatively aggressive projections, we can be half that cost. So this is some of our initial justification for kind of moving towards this path. But again, it's finding the right stakeholders and the people that will value that electricity that's being stored and will be willing to pay that cost. So this slide is just to show that there are a lot of studies out there. So whether you look at lead acid batteries, sodium sulfur, the compressed air, we have Sandia National Labs, we have EPRI, several different studies that are looking at that cost, levelized cost of electricity. And they all will have a different assumption, whether it's arbitrage, the technology maturity. But the point is that there's a wide range of costs, but it's not till you do that first pilot scale project that you really get a good idea of where those costs are going to fall out. So again, I was really focused on ancillary services, right? How do you monetize that quick reacting electrolyzer, right? Before it was just arbitrage. So if you can sell some of that service of the electrolyzer ramping up and down, the cost that I showed earlier can just get better. So it's really finding a way, right? How can you find stakeholders within the utility, public utility commissions, government, where there's grid stability as a priority? So one of our options is to test this at our Energy Systems Integration Facility. This is out at Golden, Colorado, our National Renewable Energy Laboratory. It was a $140 million facility with a distributed grid that's within this building. You can see where these trucks are that technology providers can bring their units, attach it to the grid. They can be run through various simulations, hardware in the loop, and show to various stakeholders and proof testing of equipment how it might work in the field. So it gives an opportunity to showcase these technologies before you put that unit out in the field where it's going to have a big impact for customers if it's actually going to be used. So just to showcase ESIF a bit more, we're very focused on grid optimization. And so this is a new priority for the Department of Energy. So looking at ways that we can have different technologies within renewable energy, energy efficiency, buildings, wind, solar, and so on. How do those work together in an optimized fashion for a grid that can deal with variable energy? You want to find a way, rather than just one-on-one, how does a wind turbine talk to the grid, or how does solar with an inverter and just storage for its unit talk to the grid? You want everything working together. You want communication amongst all of these. So we have these cross-cutting topics such as the control layer, the individual devices, the market and policy framework. How do these work together to give you the best grid possible? And rather than just focusing, some of the feedback at our most recent workshop is it's somewhat short-sighted to only focus on renewable energy technologies, because you're going to have distributed generation that includes fossil fuel and other technologies. And you want your entire grid to be optimized, not just the renewable energy component of it. So communication, transactive energy, we're very focused on open source and finding ways that those different pieces can talk to each other, they can be secure, and have this rapid communication, so it can self-optimize rather than for waiting for someone to individually control pieces of equipment. So that was ESIF. Jumping back to electrolyzers, we did have a couple of small-scale electrolyzers on the order of 30 to 50 kilowatts, and we're showing here that the response time is this 1/100th of a second, so it's incredibly fast compared to other power generation options. So it's very similar to what a battery or a flywheel might produce, but it can be a much longer duration. So we have regulation, load following, spinning reserves, non-spinning. We have both PEM and alkaline, and you can see that they're very similar. Traditionally, you think of PEM as being much faster reacting, and maybe it's just at this smaller scale, but I think both alkaline and PEM can provide some of these services. And just to drill into this a bit more, I'm just about done. This was looking at the response time. So if you have the unit at some 25%, 50%, or 75% part load operation, how fast does it take for it to ramp up to 100%? And then vice versa if you want to ramp down. So the left side, you can see it ramping up. And again, it's this sub-tenths of seconds level where it can respond and reach the target set point. And then the same on the decrease, so the ramp down. It's very, very fast responding. So we've showed this over the last 5 years on smaller units, 5 kilowatts, and kind of progressively moving up. But we're hoping at this year to test kind of on the order of a megawatt scale, or maybe some 1/8, 1/4 scale megawatt system. So we're providing a test bed at NREL, and we're looking for different electrolyzer companies to come showcase their products and find a way where we can get stakeholders from various utilities, public utility commissions that mandate how ancillary services are valued, gives an opportunity for them to show that. So hopefully by the end of this year, we'll have some reports that can be shared publicly. So the last part, I had talked about this previously, just how do you value that energy storage? So I think electrolyzers have a lot of value to the grid, but if you're turning that electricity back, hydrogen back into electricity, you have a very low efficiency, right? It's just not very economic. But if you can look at that going to hydrogen as a fuel, it can be much more valuable. So I'll focus here. There's no hydrogen sale on the left side, and you can see the ancillary services revenue in the blue bars is relatively small, very small, versus the costs. On the middle scale, we have a 100 kilogram a day hydrogen refueling station, and you can see still the revenue doesn't quite overlap. And those bars are based on either optimistic or high and low hydrogen fuel sales at $3 to $10 a kilogram. But then if you look over on the right, rather than using just this base load of steam methane reforming or a fuel cell turning it back into electricity, over on this right side, your focus, it's mostly just electrolyzers. And that's where we're seeing this overlap and this initial opportunity to really make a profit on that hydrogen production and monetizing those grid services. So this is focused on 2012 California data. It's a Plexos modeling that's fairly sophisticated. It's got time of day pricing and so on. But I'd be happy to share more. Josh Eichmann is an NREL fellow. He's been with us for 2 years, and we're hoping he'll maybe come over to DOE. We'll see. But he's done a lot of the work in showing this happen. So just to finally close, so hydrogen fuel. Well, who needs hydrogen fuel? You start looking overseas, and there's a lot of Germany, Japan, they're saying, well, we need 100 refueling stations, we need 50 refueling stations by 2016. But when you look at the policies driving the need for those zero-emission vehicles, it's kind of on faith. When you look to California, the zero-emission mandate, vehicle mandate started in 1990, and every 2 years it's up for review. But the purpose of that was to force the auto manufacturers to provide some percentage of their sales as zero-emission vehicles. And if they don't provide those vehicles, there's a $5,000 fine that they have to pay for each car that's not sold. So if you followed the news, there was some discussion between Tesla and who's getting credits and how do you make it work out. But this is the policy hammer that's pushing things forward on the technology side. So you look over here, the zero emission vehicle requirements, there's projected here. The ZEVs can either be battery electrics or it can be hydrogen, and it's up to the auto manufacturers to decide that mix that works for them. You can see here in 2018, things start to ramp up. We still have a lot of plug-in hybrids, but all of that works together to reduce the costs of batteries, the electric drive chain, all of that is moving California forward. So the three things that they have, the zero emission vehicle mandate, they're targeting a 1.5 million infrastructure for 1.5 million ZEVs by 2020. And then they have an 8-state memorandum of understanding to get on the order of 3.5 million zero emission vehicles on the road by 2025. And again, that can be a mix of either hydrogen fuel cell or electric vehicle. Over on the right, for that REPS standard, this is this energy, a study by Energy Environmental Economics. This is a utilities commission this study, and it's trying to understand what are they going to be on the hook for after 2020, right? What's going to happen after 33%? It's already a very aggressive target. And what they're showing here is that with large percentages of solar, there's almost 12,000 gigawatt hours of overgeneration. There's a tremendous amount of curtailed energy projected as you get more than can be used during kind of midday use patterns. But the challenge there is that if you look at the actual percent of the hours or the hours per year, it's very low, right on this order of 800 hours out of 8,000. That's not enough to run a business case with such a low utilization. So right now, California is thinking very hard, how do you deal with demand response? What are all the tools in their toolbox to encourage and incorporate quite a bit of renewable energy? You can see the ramp up of fuel cell electric vehicles. This is from a 2010 survey from the auto manufacturers. The lower left corner, it's a bit out of date, but I think they're going to release a new survey here shortly. But this is to give some idea of what they're planning if the infrastructure was available. And the last one is just on the side, there is a renewable energy hydrogen mandate in California. So when they reach a certain number of tons sold per year, so 350 tons per year, there has to be a 33% renewable energy content to that hydrogen. So whether it's landfill gas or electrolytic, however it happens to be provided. But you say, well, we're not going to reach that demand for another 10 years, or it's going to be a while before we need that. But for any of the publicly funded stations, they're already required to meet that mandate. So renewable energy and hydrogen is already in the mix in California. And maybe they're starting at 9 stations and they're trying to get to 100 by 2015, 2016. But the state funding is there, and it's likely to happen. We're just waiting on the cars, I think, at this point. So I have a little bit about footprint, but we have hydrogenics, we have proton. Both are moving towards a standardized ISO container. This was try to get an idea of how much you might need to store and what the footprint might be. But over on the left is an Olympic-sized swimming pool here, and that's probably worth 40 days of storage at 100 bar. But I'm not going to go into this now. I think I'll jump forward. The last item, if you're working in the area of energy storage and you might be in California mid-May, we're going to have a hydrogen energy storage workshop. So it's going to be focused on policy drivers, where are the technology gaps, and what's needed. And this is being done with Industry Canada, co-hosting this at the California Energy Commission, so mid-May. So, and the last thing, it's focused on both the grid and transportation support. So I think I may have gone over time, but I'd be happy to take questions.
Thank you very much, Dr. Gardiner, for your very excellent presentation. Are there any questions from your side? So please raise your hand. I'll come directly to you. If you would please introduce you, please.
Can you mention where you're from and who you represent?
My name is Lawrence Grant Clements. I'm working for my own company that is called Percy. You described the hydrogen economy connected to the grid split into 5 layers. You know, like the market layer, system control layer, cyber layer, local control layer, device layer.
Right, this optimized grid.
And which layer do you think is the less mature?
That's a good question. They all need to be done, right? In order for the optimized system, right, you're going to need the communication cyber layer. You're going to need the technology to be commercially available. Pardon me?
You focus on the device?
Yeah, we focus on the device. All the discussions here are really on the device, but not on the system controls and on the other layers. And we see less companies being involved in managing a grid that involves hydrogen. And I was wondering whether in the US you would see a lot of companies getting into these developing solutions for the different layers that need to be encompassed for this overall system.
Yeah, absolutely. I think that it's very important as we look forward that those behind-the-scene companies that are not as well known, right? They need to be able to have their products be tested and get through that R&D phase so that it can be brought to market. But whether it's the policy framework, all of this can take a long time depending on the development cycle to get it ready. So I think we're working on all of those layers, and I apologize, I don't have a good answer on which one needs the most work. I think it's good to point out that the communications and those suppliers of those devices maybe have been left out, but that's why we're starting this project to ensure we get as broad an input as possible in kind of where the gaps might be.
Any more questions from your side? Well, yes, there's one more. Please introduce yourself.
Hi, my name is Natarajan. I'm from India. The question that I have is on the layers question again.
Let me see if I can jump to that slide. It wasn't working earlier.
Just give us a second.
Oh, okay. Maybe in the back they can jump. But go ahead. Your question was on the layers.
The question is, it's a little clear as to the bottom layer, as you know, for example, what companies and all that. But my question is, who are the people or who are the companies or the groups or the government involved in the other layers? Would that be industry groups and the government?
Yeah, so we have multiple industry stakeholders. I'm a little less engaged since I have tunnel vision just on the hydrogen side of it, but whether it's a Smart Grid Alliance, if you go to the DOE website or Office of Renewable Energy, Office of Electricity and Reliability, they have various working groups that are kind of ways for industry stakeholders to get together and kind of have that discussion on what needs to be done. I don't know if I haven't answered your question very well, but I think there are other parts of DOE that are kind of working on that to make sure all the stakeholders are at the table.
Any more questions from your side? Well, if I may, I just wondering, the shale gas boom we see in the United States,
right.
is that affecting also the renewable energy part? Because United States, they get to every CO2 reduction focus that they ever wanted to just by taking natural gas now.
Right. So I think that in some ways it is challenging. I mean, some of the benefits are natural gas can load follow renewables. So in those states, right, so California has 60% of the shale gas resources of the US and it hasn't been tapped. But they have a very strong renewable energy focus, and so it's going to be interesting to see how that plays out. So one, natural gas can load follow renewables, so that's complementary. If we look to some of the issues around CO2 and methane, right, they're flaring a tremendous amount of resource as you look at, billions of tons per day being just flared because there isn't infrastructure there to take that natural gas. So I think that we're still coming to terms with how to manage the energy. If you look to shale oil, the natural gas is a byproduct, so in some ways it's in the way. So I think we will figure out a way to implement it. But those states, right, the Northeast, California, Hawaii, those that are very focused on renewable energy will continue to push forward. And at some point, right, that natural gas does provide a low-cost hydrogen stream. So.
Very good. Thank you very much.
Yeah.
If there are no more questions from your side, I would like to thank you once more, Dr. Gardiner, for being here. It was a pleasure having you here on stage.
Oh,
and
of
thank
course.
you very much for your attention.
Yeah,
thank you
thank
very
you.
much.